In mathematics, Machin-like formulae are a popular technique for computing pi to a large number of digits. They are generalizations of John Machin's formula from 1706, which he used to compute pi to 100 decimal places. Machin-like formulas have the form, wherein a positive integer such that is assigned non-zero integer, and as a positive integer. These formulae are used in conjunction with the Taylor series expansion for arctangent derivation. In angle addition formula we learned the following equations. Simple algebraic manipulations of these equations yield the following. If all of the Machin-like formulae can be derived by repeated application of this equation. As an example, we show the derivation of Machin's original formula. An insightful way to visualize equation 2 is to picture what happens when two complex numbers are multiplied together. The angle associated with a complex number is given by. Thus, in equation 3, the angle associated with the product is. Note that this is the same expression as occurs in equation 2. Thus equation 2 can be interpreted as saying that the act of multiplying two complex numbers is equivalent to adding their associated angles. The expression is the angle associated with. Equation 1 can be rewritten as where is an arbitrary constant that accounts for the difference in magnitude between the vectors on the two sides of the equation. The magnitudes can be ignored, only the angles are significant. Using complex numbers, other formulas may be generated using complex numbers. For example, the angle of a complex number is given by, and when you multiply complex numbers you add their angles. If A equals B then is 45 degrees or. This means that if the real part and complex part are equal then the arctangent will equal. Since the arctangent of one has a very slow convergence rate, if we find two complex numbers that when multiplied will result in the same real and imaginary part, we will have a Machin-like formula. An example is an. If we multiply these out we will get. Therefore, if you want to use complex numbers to show that, you first must know that when multiplying angles you put the complex number to the power of the number that you are multiplying by. So, and since the real part and imaginary part are equal, then two-term formulas. In the special case where is 1, there are exactly 4 solutions having only 2 terms. These are Euler's, Hermann's, Hutton's, and Machin's. In the general case, where the value of is not restricted, there are infinitely many other solutions. Example. The adjacent diagram demonstrates the relationship between the arctangents and their areas. From the diagram, we have the following. More terms. The 2002 record for digits of pi, 1,241,100,000,000, was obtained by Yasumasa Kanada of Tokyo University. The calculation was performed on a 64-node Hitachi supercomputer with 1 terabyte of main memory, performing 2 trillion operations per second. The following 2 equations were both used. Kikuo Takano, F.C. M. Stormer. The most efficient, currently known Machin-like formulas for computing pi. Efficiency. It is not the goal of this section to estimate the actual runtime of any given algorithm. Instead, the intention is merely to devise a relative metric by which two algorithms can be compared against each other. Let be the number of digits to which is to be calculated. Let be the number of terms in the Taylor series. Let be the amount of time spent on each digit. The Taylor series will converge when. Thus, for the first term in the Taylor series, all digits must be processed. In the last term of the Taylor series, however, there's only one digit remaining to be processed. In all of the intervening terms, the number of digits to be processed can be approximated by linear interpolation. Thus, the total is given by. The runtime is given by. Combining equations, the runtime is given by. Where is a constant that combines all of the other constants. Since this is a relative metric, the value of can be ignored. The total time, across all the terms of equation 1, is given by. Cannot be modeled accurately without detailed knowledge of the specific software. Regardless, we present one possible model. The software spends most of its time evaluating the Taylor series from equation 4. The primary loop can be summarized in the following pseudocode. In this particular model, it is assumed that each of these steps takes approximately the same amount of time, depending on the software used. This may be a very good approximation or it may be a poor one. The unit of time is defined such that one step of the pseudocode corresponds to 1 unit. To execute the loop, in its entirety, requires 4 units of time, is defined to be 4. Note, however, that if is equal to 1, then step 1 can be skipped. The loop only takes 3 units of time, is defined to be 3. As an example, consider the equation. The following table shows the estimated time for each of the terms. The total time is 0.75467 plus 0.54780 plus 0.60274 equals 1.9052. Compare this with equation 5. The following table shows the estimated time for each of the terms. The total time is 1.1191 plus 0.8672 equals 1.9863. The conclusion, based on this particular model, is that equation 6 is slightly faster than equation 5, regardless of the fact that equation 6 has more term. This result is typical of the general trend. The dominant factor is the ratio between in. In order to achieve a high ratio, it is necessary to add additional terms. Often, there's a net savings in time.